Alright, if we're trying to find the greatest common factor of 3 or more numbers, it's the exact same technique as with 2. That's one of the nice things about the method that I just went over. So 24, we need to find the prime factorization here. This is 3 times 8, so 3 times 2 cubed. 40 is 8 times 5, so 2 cubed times 5. Again, I'm going down to the prime factorization. This is why I'm not comfortable, and this is why I don't just leave that as an 8. I'm calling it 2 cubed. And then 72 is 2 cubed. It's 8 times 9, so 2 cubed times 3 squared. My greatest common factor, I'm going to look through each of these bases and see, well, okay, 2 occurs 3 times in each of those. So I get 2 cubed as part of my greatest common factor. For 3's, I don't have any 3's here, so that means it's not part of my common factor. And for 5's, I don't have any 5's in, well, this one, or that one for that matter. So 5 is not part of my greatest common factor. So it looks like my greatest common factor here is just 8. We can do the same thing if there are variables present. This is a big reason why we're doing it this way. 8y to the 4th, this is 2 cubed times, well, actually, let's first figure the greatest common factor of 8 and 12. It's small enough, it's easy enough to do. The greatest common factor there is 4. But you could do it the same way. You could say 8 is 2 cubed, 12 is 2 squared times 3. So the greatest common factor of these is 2 squared, so that's equal to 4. But actually, we're not just doing 8 and 12. We're doing 8y to the 4th, and we're doing 12y squared. So I can just tack those on in the exact same way. And you can see if we're looking at the bases, y also occurs twice. So our greatest common factor here is 4y squared. Alright, if we have 3, again, it's the same sort of technique. 3x cubed. There's no prime, that's already a prime factorization, essentially. 9x squared is 3 squared times x squared. And negative 21 is 3 times 7 times x. So my greatest common factor here, look through all the bases, I can see a 3 occurs once on all of them, and I am limited to 1 copy of the 3. And 7 doesn't occur on all of them, so I can't include that. But x does occur on all of them, and it looks like I'm limited to 1 copy of the x. So my greatest common factor here is 3x. I'm going to just ignore the fact that there's a negative there. On some of these, we will see the negatives will be important, but for now, it's not part of just our greatest common factor. All right, for this one, well, looking at the 10, the 15, and the 25, hopefully you should be able to see this pretty quickly. This is 2 times 5, that's 3 times 5, and that's 5 times 5. So my greatest common factor, the coefficient of my greatest common factor at least, is just a 5. Then I'll look through my x's. There's 5 there, 2 there, 3 there. I'm limited to the 2 on the second one. And then looking at my y's, I have 4 there, 3 there, 5 there, so this is limiting me to the 3 copies of the y. So my greatest common factor is 5x squared y cubed. Alright, on this one, it actually doesn't matter if the individual factors are more complicated. So in this instance, you can see they both have an x minus 1. Since x minus 1 is a factor of both of these, it is then a common factor. So that means the GCF here would be x minus 1. You'll see there's nothing else in common between the 3 and the 8. 3 is prime and 8 is 2 cubed, so there's nothing else in common between them. That's why I say the greatest common factor is just x minus 1. On this one, it looks like, let's see, between the 2 and the 4, there's a common factor of 2 because, well, 2 goes into 4. So we get our greatest common factor includes a factor of 2. Looking at the z plus 3 is not common in both of these. So z plus 3 is not a common factor, but z plus 5 is common in both. Actually, I have 2 copies of the z plus 5 in this second one, but I'm limited to only having 1 copy in my greatest common factor because of the first one. So this is going to be 2 times z plus 5. That's my greatest common factor of these two expressions.